welcome to Math 150, Section 2, Lecture 24, 2021. Continuing the streak of reading what I wore in 2014. I thought my days of having to get into the T-ball shirt for my daughter's team were long gone. I'm not sure actually which is more uncomfortable right now, the mask or the shirt. So today, that uncomfortability, if that's a word, is actually, I think, a nice segue into what we're doing today, which is trying to figure out which test should we use and when to determine whether or not a series converges or diverges. And I have hopefully given you the newborn baby metaphor earlier. When you have a newborn baby and it's crying at first, you don't know why it's crying, so you have a list that you try. And eventually you start to hear that there is a difference between the I'm hungry cry and the I want to be held cry. And then as the baby grows up, you completely blank out those years from your life and you forget all those. But at one point in your life, you know those really, really well. It's the same way when you do stuff like this. The more time you spend on these problems, the faster it will be for you to quickly look at something and recognize which test should you use. What's nice is the number of tests we have can essentially be counted on one hand, maybe with a few friends from the other, but not too many. We don't have that many things to try. So if something doesn't work, move on, try the next one. If I give you a quadratic, and this quadratic comes from the real world, my go-to would be to use the quadratic formula, because it is extremely unlikely that a real-world quadratic is going to be really nice. But if I give you a quadratic from an algebra class, almost surely this will be a very nice one that I can see easily, or after quick inspection, I know it won't be done that way and I have to use the quadratic formula. So you should have a couple of go-tos. The comparison test is really nice, it's really powerful, but the challenge is when you're using the comparison test, you have to know what to compare it to. And you're not told. You can compare it to anything. So the more things you know, the greater the chance you have of being able to use the comparison test well. To do the comparison test well, often you don't look at the initial sequence, you often look at a modification. And we'll look at some modifications of sequences later today. If something if something converges, what you can often do is look at something that's a little bit larger, that might be easier to analyze, and if that still converges, then you know the original one converges by the squeeze or the sandwich theorem. Similarly, if you think something diverges, you can look at something that's a little bit smaller, but maybe easier to look at. And so for a lot of these things, rather than looking at what you're initially given, it might be better to look at something similar and closely related. Okay, so now let's start off with the ratio. So the ratio test and the root test are extremely powerful, and what they're really doing is they're really an application of the comparison test. So the comparison test, you can use any sequence. Ratio and the root test are comparing things to a geometric series. A geometric series with ratio rho, where rho is the limit of some process. And what's nice about the ratio and the root test is they calculate that limit for you and they say, use this comparison. They're telling you what sequence to use for the comparison test. So it's a little bit restrictive, but it does a lot of the calculations under the hood. If you can do some algebra, you're in great shape. Now, if I give you a sum, what's the first thing you should check if you want to see if the sum converges? So we have a 0 plus a 1 plus a 2. What's the first thing that must be true if the sum is to have a chance of converging?
The terms must go to 0.
The terms must go to 0. If the terms don't go to 0, it's not even worth trying to discuss here. Should I use the ratio test or the root test? Don't use any of them. Right? First thing to look at is, do the terms go to 0? After that, then you can start looking at what happens. So if you want, I could assume I'm doing the ratio test where a n goes to 0. It's not always going to be the case. If I have a n's that are not going to 0, the ratio test will hopefully just yell at me, it's clearly diverging. So I'll assume we might be in a situation like that. Now, the ratio test says rho is equal to the limit as n goes to infinity of a n plus 1 over a n. And there's two ways to actually write the ratio test. And since you are section 2, we will do what we did in section 1. Right. So I can take the absolute value here and then say is row strictly less than 1, equal to 1, or greater than 1? Or I could calculate this and then look at the absolute value of row. Well, it doesn't really matter when I take the absolute value. I can take the absolute value and then take the limit, or I can take the limit and then take the absolute value. They're not going to change. And so they decided in section 1, let's just do the absolute value from the beginning. And now row is going to be non-negative. And so we'll calculate the following. As soon as you see an plus 1 divided by an, you should be a little nervous. What is worrying you? What are you afraid of? Yeah, an is 0. So somebody give me a sequence that converges, a sum that converges. Yeah, I was wondering if I was going to have a smart ass. Yeah. So 0 plus 0 plus 0 plus 0 goes on. Give me another one that's not all 0 terms.
1 over n squared.
1 over n squared, okay. So we can do 1 plus 1, 4 plus 1, 9. And this is actually pi squared over 6. A beautiful result with lots of applications. Now, if you notice, something seems to be wrong the way I wrote this. I've got all this blank space. Well, we shouldn't leave blank space, we should fill it. Let's put in some zeros. So I will put infinitely many zeros in. Am I going to change the value of the sum? No. So when I have my sequence, if my sequence has any terms that are 0, I might as well remove all those terms from the sequence, because they're going to just screw up stuff like this, right? So you might as well assume the terms are non-zero. So we'll assume either an is not equal to 0 or an is greater than 0. Because if you look at how we're doing the ratio test, we're looking at the ratio of an plus 1 over an. It doesn't really matter what the sign is of an. I'm taking absolute values. So if you want, you might as well assume every term is positive. And this is a standard process. You take what you're given and say, well, without loss of generality, it's enough to consider this. Without loss of generality, it's enough to consider this. Eventually, you get to something that you must consider. But you can go a long ways before you actually have to do any work and say, let me put in some simplifying assumptions. Which great New England transcendentalist writer does this remind you of? Henry David Thoreau. In fact, my wife and I were hiking in the southern Berkshires this weekend, and we actually came across, at the very top of one of the mountains, a rock bench with a quote from Henry David Thoreau. Sadly, it wasn't one of my favorite quotes. It was not the simplify. It was far too long for me to really remember here about, but it was nice to see Thoreau. You should always, always, always think about Thoreau before you do any algebra. Before you start doing a long calculation, it's worth taking a moment or two and seeing, can I do a related problem? Can I simplify it that will make it a lot easier before I start delving into long algebra? And I will do a problem like that later today to just really drive it home. So we'll have row with its limit. If row is less than 1, it converges. If row equals 1, no information. And if row is greater than 1, it diverges. And we're talking, of course, about the infinite sum, n goes from 1 to infinity of a. So that sum will converge if row is less than 1, diverge if row is greater than 1, and we don't know what happens if row is equal to 1. So I will do a brief sketch of why this is true. Do you want to see the sketch in the case of diverging or converging? Diverging. Okay. So this is good. This is the opposite of section 1. Section 1 wanted to see converging. I don't know if this means anything deep about the two classes, if this is the more divergent class. But what's nice now is we now have both cases. So we will do assume row is greater than 1. So that means there exists an n such that for all n greater than or equal to n, the ratio an plus 1 over an is going to be greater than or equal to 1 plus epsilon for some fixed epsilon greater than 0. So let's just unwind what that means. Here's 1. Here's rho. Rho is some number greater than 1. Somebody give me a number greater than 1.
1.1.
1.1. So I can choose a really small epsilon, 1.001. And now whenever little n is sufficiently large, my ratio is going to be very, very close to rho. So close that it's larger than 1 plus epsilon. This will be my 1 plus epsilon. What I'm basically saying is, look, if I'm greater than 1, I'm greater than a number that's greater than 1. So this may not be true for all values of n, but from some point onward, it has to be true. Okay, is everybody comfortable with this? So now let's look at what's going on. An plus 1 will be over an, which is capital N. That's going to be strictly greater than or equal to 1 plus epsilon times an. I'm sorry, 1 plus epsilon, which means an plus 1 is greater than or equal to 1 plus epsilon times the absolute value of an. Now let's look at an plus 2. So an plus 2 over an plus 1 is also greater than or equal to 1 plus epsilon. Right? Because we're told that the limit converges to rho, and so eventually it's greater than 1 plus epsilon. So that means an plus 2 is greater than or equal to 1 plus epsilon times an plus 1. But what do we know about an plus 1? So what do we know about an plus 1? Almost. You used the word equal. It's greater than or equal to. We know an plus 1 is at least 1 plus epsilon times an, so we get an plus 2 is at least 1 plus epsilon squared times an. Similarly, what do you think would be true for an plus 3? It would be at least 1 plus epsilon cubed times an. And since an is not 0, what happens is you take 1 plus epsilon to a higher and higher power. It increases. So it's going to go off to infinity. So my terms can't go to 0. So it's divergent. So an goes to infinity, diverges. If we did it the other way, for conversion, you would have it would be less than or equal to 1 minus epsilon, and you'd have an plus 3 is less than or equal to 1 plus epsilon cubed times an, and it'd be a geometric series that bounds it. So what's nice now is each section can just fast forward to the other section to see the other side of the argument. But here, we're able to show that the series diverges. And so this is why the ratio test works. Let's apply the ratio test. So let's let an equal 1 over n factorial. So n factorial is n minus 1, that is off 3 times 2 times 1, 0 factorial equals 1. So the geometric interpretation, or the combinatorial interpretation of n factorial is it's the number of ways to order n objects in order matters. So if you have offices for a club, there's a difference between president, vice president, and so on. So if you have 5 people, there may be 5 ways to choose who's president. And then of the remaining people, you have 4 people left. You have 4 choices of who becomes vice president, and 3 choices of who becomes treasurer, 2 choices of who becomes secretary, 1 choice of who becomes pizza president, which is probably the most important role in many organizations. So n factorial is extremely important. It arises in a lot of problems. And you can ask, does the sum of 1 over n factorial converge? So whenever I do these problems, I like to be extremely explicit and start off by writing things such as, I'm going to use the ratio test. I'm going to look at the limit of an plus 1 over an. Don't just have math erupting on your paper, especially on an exam. Do you think that I can look at your exam and figure out what you intended?
Yeah.
Well, it's how much confidence do you have? I've been teaching multivariable calculus since the 90s.
Yeah.
So yeah, I've been doing this since before you were born. Okay? I should be able to look at your paper and figure out what you meant. But I have to go, when I'm grading, based on what is there. And you always want to make it as easy as possible for people who are looking at your work to know what you're doing. Take the time and clearly write what you're doing. You're also much less likely to make a mistake when you put in all the structure. If you're going to use integration by plots, write down everything before you use it. Here's u, here's dv, here's du, here's dv, here's integral, there's plot, is uv at the boundary minus v du, blah, 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 blah. The more stuff you put in, the less likely it is that you're going to make a mistake, that you're going to forget a step. So I'm going to just go through this very slowly methodically. This is the limit as n goes to infinity. So an plus 1 is 1 over n plus 1 factorial divided by 1 over n factorial. That's the same as the limit as n goes to infinity of 1 over n plus 1 factorial times n factorial over 1. And you'll see later why I'm writing it like this. I'm going to be taking advantage of the fact that I'm at a blackboard to do the next problem very quickly. What's n factorial divided by n plus 1 factorial? One over n plus 1. So this is just the same as the limit as n goes to infinity. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2. Oh, from this point onward, it's just n factorial. And we see that the n factorials cancel. So this is just the limit as n goes to infinity of 1 over n plus 1. And what's that limit going to be? So as n gets very, very large, 1 over n plus 1 goes to
0.
0. So I've got 0, I've got 1. Right? So as n gets very large, 1/10, 100, 1,000, 1 million, 1 billion, 1 trillion, it's just going to go to 0. So it converges. So this tells us the sum of 1 over n factorial converges. And it actually converges to a very famous number, which we'll see in a moment. I want to make sure there's no questions on this before I do a slight modification of the board. So is everybody comfortable with what we have so far? What I want to do now is I want to look at infinitely many generalizations all at once. And so instead of looking at 1 divided by n factorial, I'm going to generalize this, and I'm going to use the fact that I'm at the blackboard and do x to the n over n factorial. And you can just copy this from the video later. So when you look at x to the n, if x is a large number like 10 or 100, as n gets very, very large, what happens to x to the n? What's it doing? It's getting big. So x to the n is exploding. But n factorial, we know, is getting very, very large as well. So large that the series converges. So the question is, which is growing faster, x to the n or n factorial? And so there's a lot of ways to do this. I'm going to first show you how to do this using the ratio test. And then I'm going to show you how to do it using the comparison test. And I will ask you, which way do you think is harder? Right, well, let's look at how much things change. Does this? No, this doesn't change. This is the definition. So now I have, instead of 1, I have x to the n plus 1, and I have x to the n over here. Okay, so this 1 becomes an x to the n plus 1. This becomes an x to the n. What's x to the n plus 1 divided by x to the n? It's just x. So when I have x times this, x is fixed. Can I pull the x outside the limit? If you have a limit that has a certain value, if you multiply every term by 16, the limit changes by multiply by 16. If you multiply by 1/3, it changes by multiplying by 1/3. So I could pull the x outside and I could write the x over here, almost like there's space for this to be written. Or if I wanted to, I could even leave it over here. Because x is fixed, what happens is then goes to infinity. It's still 0. So this tells us that the sum, and it goes from 0 to infinity of x to the n over n factorial, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, converges always. And this is one of the definitions of the exponential function, e to the x. It's an extremely important function. We'll see later today another definition of e to the x, the compound interest one. How many of you have seen the compound interest approach to the exponential? Your bank which gives interest compounded continuously. Okay, any questions on this calculation? I'm going to show you another way to show that it converges. So an is 1 over n factorial. Do you agree that this is less equal to 1 over n times n minus 1? At least if n is big. What does big mean? This will actually work for all values of n. If you take n equals 1, you get 1 over 1 factorial is less than 1 over 0. Okay. But once n is 2, it's more reasonable. Why is this true? Well, n factorial is n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. Once n is 3, I'm dropping terms. If I drop terms in the denominator, if I make the denominator smaller, what does that do to the fraction? Makes it bigger. So I believe that this sum converges. So because I believe it converges, I believe I have a little wiggle room to play with. And so I'm going to try to approximate with 1 over n minus 1. Well, this is plus equal to 1 over n minus 1 squared. Because I'm replacing n with n minus 1. So again, I'm making the denominator smaller. So if I make the denominator smaller, I'm going to make the fraction bigger. On Monday, I'm going to do, as part of the review day, a review of logarithms, exponent laws, and whatnot. I found over the years that's actually a good thing to do, and so I will actually have some slides for that. I now get the sequence 1 over n minus 1 squared. Any idea what we should compare this to? Yeah, it's 1 over n squared. It's just shifting everything by 1 unit. So converges by comparison. So which proof do you think is easier, the ratio test or the comparison test? So for the comparison test, I had to figure out that I can replace the n factorial with just 2 terms, and then replace those 2 terms with just the second one squared. If you can see something like that, it's actually much nicer, I think, than doing all the algebra. You know, I deliberately wanted all of this to be on the blackboard simultaneously, so you can see the difference. You know, I'm able to do this in a really small space over here. But you have to see all this. And the more problems you do, the easier it will be to see something like that. Okay, any questions about this? And for those of you who are not enjoying these examples, just remember I have to do this twice each day. In the fall, the professors have to do it 3 times. So it could be worse. All right. So what I want to do now is I want to do a more interesting example. And what should be the first thing that goes into your mind that you want to do when I write down the example? What should go to first step, first thing you look for?
Make sure it goes to 0.
Make sure the terms go to 0. If the terms aren't going to 0, it's not worth doing anything further. So let's let an be 2 to the n plus the square root of n plus 4 divided by the square root of n factorial. So hopefully this is nasty enough that you don't have a great intuition of what's happening. Or maybe you do. Do you think this converges or diverges? What governs the numerator? The large n, which is more important, 2 to the n or the square root of n plus 4? 2 to the n. You give me an upper bound for the square root of n plus 4. How large could the square root of n plus 4 be? So this is the danger. If you're comfortable with algebra, you can look at these expressions and hear them. You can do a lot to make your life easy. I claim that the square root of n plus 4 is at most n plus 4. Because if I just increase the n to n plus 4, I have the square root of n plus 4 squared. So this is going to be equal to 2 to the n plus n plus 4 over the square root of n factorial. And do we agree that when n gets really, really large, 2 to the n is larger than n plus 4? So to be safe, this is what's equal to 4 times 2 to the n over the square root of n factorial. We know if we had 2 to the n over n factorial wins. That's what we just did. If we just did x to the n over n factorial, that would be the case x equals 2. But we don't have x to the n over n factorial. We have x to the n, 2 to the n, divided by the square root of n factorial. If you have a really, really big number, what happens when you take the square root? Small. So would you be happy if I deposited $10,000 in your bank account? Yes. What if I deposited the square root of $10,000? You'd still be happy, but what's the square root of 10,000? 100. Right? And if I deposited the square root of 100 into your bank account, we're now talking about $10, basically a lunch. So as you take more and more square roots, you can really shrink down the size. So how big is the square root of n factorial relative to n factorial? Well, the square root. Is it so small now that 2 to the n wins? Or is n factorial growing so rapidly that even if I take the square root, well, let's rewrite this. Let's say I want to write 2 to the n as the square root of y. What would y have to be if I want 2 to the n equals the square root of y? 2 to the 2n. So y is 2 to the 2n or 4 to the n. So this is the same as 4 times 4 to the n over the square root of n factorial. I'm sorry, the square root of 4 to the n. Or it's 4 times the square root of 4 to the n over n factorial. Yes?
Why are we multiplying by 4?
Because I want to be safe. When n equals 1, which is larger, 2 to the 1 or n plus 4? N plus 4 is larger. So I have to put a little fudge factor if I want this to hold for all integers. But the other thing, even if I didn't put in the factor at all, it's no longer correct because the n plus 4 makes it a little bit higher. So I have to put in something. I don't care what constant I put in here, that's not going to fundamentally change anything. So I just put in something so I'm safe. And now I know 2 to the n plus n plus 4 is always going to be less than or equal to 4 times 2 to the n. And so I'm fine doing that kind of simplification. Does that make sense?
Thank you.
Good. Now the question is, what could I use a smaller number? Could I use 3? Absolutely. 2. Well, the smaller the number, you get to the point where it works only for all insufficiently large. I could use 1.1. but I would now have to have n be much, much larger for that to fit. So when you look at this, this is, hey, that's the ratio we just calculated before. You know, the ratio of 4 to the n over n factorial was just 4 over n plus 1 when we used the ratio test. So we would now get the square root of what we had before. Well, what we had before was going to 0. So if something is going to 0, what's its square root going to? 0. So we could do the ratio test. And again, we have the square root. We could ignore the square root and then just take the square root of the limit. So that's one way to approach this problem. And so if you look at what I did is, I actually did a comparison test because we now know that x to the n over n factorial converges. And so I can now compare things to that. And so by knowing the comparison test, that was fine. Well, if I want to, I can do a ratio test again. And when I'm doing the ratio test, I just have to take the square root of things. Okay. To do this, I had to have some comfort with algebra. And I had to be able to look at things and see the relationships. If you don't see this, what do you need to do?
You know.
You need to do what? You need to roll up your sleeves and do the algebra. So rho equals the limit as n goes to infinity, absolute value of an plus 1 over a. All start that way. And now let's just go through the algebra and see can we get it to work. So when we put in n plus 1, it's the limit as n goes to infinity. And when we put in n plus 1, we're going to have this in the numerator, it's going to be 2 to the n plus 1 plus the square root of n plus 1 n plus 5 divided by the square root of n plus 1 factorial. Then we divide by an. Well, dividing by this is the same as multiplying by its reciprocal. So just to save a little bit of space, it would then be the square root of n factorial at the top, and then 2 to the n plus the square root of n plus 4. What's the square root of n factorial divided by the square root of n plus 1? Yep, so you have it's the limit as n goes to infinity of 1 over the square root of n plus 1. And then we have 2 to the n plus 1 plus the square root of n plus 1 n plus 5 over 2 to the n plus the square root of n plus 4. Okay. Well, this should hopefully remind you a little bit of when we look at ratios of polynomials. And we're looking at what happens as x goes to infinity. And you pulled out the highest power of both. But when I look at this, I could pull out from the numerator a 2 to the n plus 1. And what should I pull out from the denominator? 2 to the n. And 2 to the n plus 1 divided by 2 to the n is 2. So this would then just become the limit as n goes to infinity of 2 over the square root of n plus 1. And then when I pull out 2 to the n plus 1, I get 1 plus the square root of n plus 1, n plus 5, divided by 2 to the n plus 1. I have 1 plus the square root of n plus 1 over 2 to the n.
Why is it now n plus 1?
Because I have made a mistake. It should be n plus 1. We now have a limit of a product. What is a limit of a product? So the limit of a product is the product of the limits, so long as you are not in an exceptional case. In what case do you have to avoid like the plague? There's one case when you're not sure that the limit of the product is the product of the limits. So which two numbers can you not multiply and know what the answer is? 0 and infinity. So if it's 0 times infinity, we're in trouble. Well, fortunately, this limit is finite. As n gets very, very large, what does the numerator go to? The numerator just goes to 1. The denominator goes to 1. So this expression goes to 1. This expression goes to 0. So the entire limit is 0. And so the blackboard now has two different proofs that the sum converges. Which proof do you like? There's good points of each. The ratio test is in some sense more straightforward of just doing the algebra. You need to figure out which terms do you want to combine. A lot of times it's screaming at you what to combine. Look, I've got a square root of n factorial and square root of n plus 1 factorial. These two terms look so much like each other, you should put those two together. And then for this part over here, you have to see to pull out the highest power of 2 to see what things are going to. But if you look when n gets really, really large, the numerator is basically 2 to the n plus 1, the denominator is basically 2 to the n. This looks like 2. It's not going to be enough to overcome what's happening with the 1 over the square root of n plus 1. This way is a little bit faster, and it says, well, look, I have a suspicion that this is going to converge. And because I think it's going to converge, I can actually inflate the terms a little bit and look at something that's a little bit larger that will be easier to study. And because of that, I can then use a nice comparison test. Okay. Any questions about this? Okay, so again, the more problems you do, the easier it will be to see how to do the algebra. If you are not going to be a professional mathematician, if you're not going to be working in a field where you're going to be doing this all the time, it is a skill that will atrophy with lack of use. And that's absolutely fine. It's to be expected. But you'll at least know that this can be done. Algebra 1, Algebra 2 is, I think, one of the most useful classes in high school. And sadly, a lot of people are just pushed through this without getting a firm grasp of what's going on. And this is why, for the review class on Monday, I'm going to open it up to whatever you want to, but I also want to give a little bit of a lecture on logarithms. What are they good for? Why do we care about them? Where do the rules come from? I think it's going to be a good use of some time. Right. What I want to do now is prove that the ratio test cannot be the end-all, be-all. That there will be some sequences that the ratio test is just not powerful enough to handle. So does anybody remember a series that the ratio test cannot handle? AN equals, so what will give us a rho equals 1? 1 over n. Or more generally, 1 over n to the p. So if p is greater than 1, it converges. If p is less than or equal to 1, it diverges. So we showed this earlier. When p equals 1, it's the harmonic series. And we showed by grouping terms, we gave two different proofs that the harmonic series diverges. When p is greater than 1, it converges. We gave the proof in detail when p equals 2. And I argue that you could adjust that to any p greater than 1. And we did it by what's called a dyadic decomposition by looking at the integers and splitting up from 1 to 2, 2 to 4, 4 to 8, 8 to 16, and looking at how slowly things vary. We will see later when we get to the integral test that this problem is screaming at you to use calculus and is much easier with the integral test. And it'll just be a few short lines there. The integral test is a little bit different from the ratio and the root test in that you have to figure out what function to use for the integral test. Now, what's nice is in almost every case, when you use the integral test to try to find a function, what you do is you replace n with x, and that gives you your function of f of x. So for all practical purposes, the integral test is essentially the same as the ratio and the root test in terms of difficulty in figuring out what to do. So it's almost automatic what to try. All right, so let's try to calculate this. So as always, we start with rho is the limit as n goes to infinity of an plus 1 over an. It's the limit as n goes to infinity. So we have 1 over n plus 1 to the p divided by 1 over n to the p. So it's the limit as n goes to infinity of n to the p over n plus 1 to the p. This is the limit as n goes to infinity of n over n plus 1 to the p. All right, so as we go through and just start the algebra, with a little bit of time, this is what we get to. What you would love to say is the limit of the pth power of this is the pth power of the limit. If p is an integer, that's easy to do. If p is not an integer, it's not so bad if you remember one special trick. Anybody know what trick? You're just getting in the way. What trick should we use? Not multi-power, but it does start with an F. Logarithms. You should really view this as a product. Whenever you have a product, what is your go-to? Logarithms. If I look at the log of n over n plus 1 to the p, that's just p times the log of n over n plus 1. So if I know what n over n plus 1 is going to, if that has a nice limit, this is just going to p times that. So when I exponentiate it, it would just be that value to the pth power. So you can actually use logarithms to rigorously prove that if I can figure out what the limit of n over n plus 1 is, I can figure out what it is in general. So let's look at the special case p equals 1. What is the limit as n goes to infinity of n over n plus 1? So what is that limit going to be? 1. And if you think about it, you've played n plus 1 games, and you've won every game but one. As you play more and more games, your winning percentage is getting closer and closer and closer to 100%. And it will become as close as you want for any finite n. It never reaches 100%, but it gets so, so close. So this limit is just equal to 1. And so, no information. If I raise this to the pth power, again, if I go through this trick with looking at logarithms, rather than looking at this quantity, let's study the limit of its logarithm. If I know I converge to the log of 2, then if I take the logarithm, I would converge to the log of 2. Or conversely, if I know that the logarithm converges to log 2, the original sequence must converge to 2. So there's a nice one-to-one transformation. If you look at what the logarithm does, and we'll talk about this next Monday, it's sufficient to study the logarithm. And so, because the n over n plus 1 goes to 1, this is just we go to p times 1. And so when I exponentiate p times 1, it just exponentiates to 1 to the p. So, in this case, n over n plus 1 converges to 1. What's the log of 1 going to? 0. So this is still going to go to p times 0, which is still going to 0. And so when I exponentiate it, I get e to the 0, which is 1. So if p is an integer like squares, cubes, you can do it by brute force. If p equals 2, you could have n squared over n plus 1 squared, so n squared over n squared plus 2n plus 1. Factor out an n squared, you would have 1 over 1 plus 2 over n plus 1 over n squared, and that's going to converge to 1. So if n is an integer, you can do algebra like this without any trouble. I'm sorry, p is an integer. If p is not an integer, it's a little bit harder. We use the logarithm. And this example shows you that the ratio test can't handle everything. This isn't surprising because really the ratio test is comparing your sequence to a special geometric series. So if you're not comparable in a nice way to a geometric series, there's no hope. And because this converges if P is greater than 1 and diverges if P is less than or equal to 1, it means sometimes when rho equals 1, they can converge, and sometimes when rho equals 1, it can diverge. So it really is no information when we find out that rho equals 1. And so then you can ask, well, what else could we try? We could try the ratio test, or we could do that. We could try the comparison test if we can think of something good to compare it to. And then in the next class, I believe we will then do the root test. And the root test is a little bit more powerful, but the root test also has situations where it will return 1 and no information, which means you have to do something else. So again, it's like the baby crying. The longer you do this, the longer list you have of things to try, and the better chance you have of knowing what's going to work. Any questions on what we've done? All right, so this is a good place to stop. Enjoy the rest of the glorious day.